Welcome to Math 2320, Section 7.4. We look at some further properties of the Laplace transform. So, in our first property we have here, the Laplace transform of t to the power n multiplied by a function is minus 1 to the n, same n is on the power of t, and it's the nth derivative of the Laplace transform of f of t. So in our problem we have the Laplace transform of t e to the minus 5t. Alright, so we basically have this property. The Laplace transform of e to the at is 1 over s minus a. So the Laplace transform of e to the minus 5t is 1 over s minus a minus 5, which is s plus 5. So for t to the 1, that means I'm going to have minus 1 to the first power, and I've got the derivative of the Laplace transform of e to the minus 5t. So I rewrite this as s plus 5 to the negative 1. Minus 1 comes in the front, drop the exponent by 1. The derivative of the inside is just 1. So I've got minus 1 times minus 1, making it positive and giving us the Laplace transform of t e to the minus 5t. In question 2, we have the Laplace transform of t hyperbolic sine of 8t. Alright, well, we haven't used the hyperbolic sine before, but the Laplace transform for the hyperbolic sine of kt, have a k on top and s squared minus k squared. So the Laplace transform for the hyperbolic sine of 8t, I get an 8 on the top, 8 squared is 64. So it's t to the power of 1 again, so that's minus 1 to the 1. And then the derivative of 8 over s squared minus 64. So rewrite that as 8 times that thing to the minus 1. Minus 1 comes in the front. All right, got that. So I've got a minus 8, I've got a minus 1. S squared minus 64. Drop the exponent by 1, so minus 2. And then the derivative of the inside is 2s. So collecting things together, let's see what we have. Got a negative 8, negative 1, so a positive 8. 8 times 2 is 16. Have an s on the top. And s squared minus 64, quantity squared on the bottom. Alright, let's see. Here we have the Laplace transform to solve y double prime plus 16y is cosine of 4t. Got some initial conditions. Now we could solve this by what we've done previously without Laplace transforms, but let's see how we do it with Laplace transforms. So the Laplace transform of y double prime, I get s squared, Laplace transform of y, minus s y at 0 minus y prime at 0. So all of that for the Laplace transform of y double prime. 16 Laplace transform of y. And the Laplace transform of my driving function is s over s squared plus, and then the 4 squared is 16. Alright, so let's see, y at 0 is 3, y prime at 0 is 5. And to make things simpler, I'm going to call the Laplace transform of y a. All right, so collecting that together, I've got a here, a there, so that's a times s squared plus 16 equals. I'm going to bring the minus 3s and the minus 5 to the right. They become positive. And then I'm going to divide by s squared plus 16. All right, so taking it piece by piece. In this first one, I got a 3 that I can pull out, s over s squared plus 16. The inverse Laplace transform of that is the cosine of 4t. For the 5 over s squared plus 16, well, let's see. I pull the 5 out. This is a 4 squared. I need a 4 on the top. So I don't change anything. I divide by 1/4. And so I get 5/4 sine of 4t. All right, what about this piece? Let's see. Well, first off, I'm going to need a 8 on the top. Because if you look back in your back of the book for your table of Laplace transforms, when it's of this particular form, this is t sine of 4t with this constant of 1/8. So my final solution is of this particular form. All right, in question 4, they want us to find the Laplace transform of the convolution. All right, so we'll talk about the convolution in just a moment. But the Laplace transform of 1 is 1 over s. The Laplace transform of t to a power is n factorial over s to the n plus 1. So the way the Laplace transform of this convolution operation goes is it transforms into the Laplace transform of each one multiplied together. So the Laplace transform of 1 times the Laplace transform of t to the 4th. So I get a 1 over s from the Laplace transform of 1, and the Laplace transform of t to the 4th. I get a 4 factorial over s to the 4 plus 1, and 4 factorial is 24. The convolution of two functions is defined in the following way. 0 to t, f of tau, g of t minus tau. So g is delayed in time, and you're forming this integration. Where I've seen convolution used is in electrical engineering, in signal processing, and a little bit in the Circuits 2 course. All right, in question 5, they want us to perform the Laplace transform of this item, and they don't want us to actually evaluate the convolution integral. So what's going on here? Well, if you let f of t be the cosine of t, and you let g of t be 1, well, g of t minus tau is still 1. So I can recognize this as really a convolution of f and g. So it's going to be the Laplace transform of each piece. Laplace transform of the cosine is s over s squared plus 1. The Laplace transform of 1 is 1 over s. The s's cancel, and I get 1 over s squared plus 1. So the real trick here was understanding, well, what was going on in this integral? What was hiding? Because it had all the pieces, but something was not there. All right, now in this case, they're telling us that this particular integral is the inverse Laplace transform of Fs over S. So they want us to do the inverse Laplace transform for this item. Alright, so Fs over S is this item. Alright, so I'm going to solve it by partial fractions. So with this s squared, I've got an a over s. I need a b over s squared. If it were s cubed, I'd need another term. For s cubed, you count all the way up to the power. It's a repeated linear term. And finally, a c over s minus 1. And so, when we go about figuring out a, b, and c, you can let s be 1, s be 0. That'll get you b and c. That won't get you a, so to get a, what I did is I filled in b and c, and then looked to match coefficients. I know that a plus 4 has got to be 0 because there's no s squared there. And similarly here, there's no s on the left. And that gives me a is minus 4. At that point, it's easy to get the inverse Laplace transform because these are things that we recognize what they are. So some nice interesting properties of Laplace transform.